Let's think back to what happened with that kind of pre-lab problem we did about car manufacturing. We wanted to minimize square root 2x plus square root 1.9y plus 400, subject to x plus y greater than or equal to 2500, and all variables non-negative. Do you remember what happened? We found the optimal solution was to do everything at factory 2 and nothing at factory 1. And then, so here's a question, is that in the interior of the feasible region, or is that at a corner point? What does the feasible region look like? Is the feasible region convex here? And then we also tried increasing this number, and the optimal solution stayed doing all factory 2, none of factory 1, until we increased this enough, and then the optimal solution was all factory 1 and no factory 2. We never saw it somewhere in the middle, like use some of each. So can we reason why that would have been happening? And then on the electricity problem, minimizing 3x squared plus 2y squared, subject to x plus y is greater than or equal to 4, all variables non-negative. There, we did get a mix of the two as being optimal. And no matter where we started, we always found the same solution, where for this one, where you ended up for what solver thought was optimal could depend on where you started. So we could get trapped in a local min. So think about why that might have been. Well, all this and no that is a corner point of the feasible region, and we were never finding an optimal solution in the middle along the boundary of the feasible region. The objective function is concave down, square root is concave down, adding a square root to a square root, adding two concave down functions, you get a concave down function. And we could apparently get trapped in local mins, just like we said up here. And we were, our optimal solution was at a corner point. For the electricity problem, we were optimal along a boundary. Now, I'm not saying it would always be along a boundary. It could be at a corner point. It could be in the interior. But we never got trapped in a local minimum that wasn't global. And that's because we were minimizing a concave up function or a convex function. So that's why I posed those two problems, to see those two big things that happened. And then another thing we can look at, way back when we talked about an inventory production planning problem. And when we had ordinary overtime going on, like overtime costs more than regular time, we made a graph in the homework of what it, actually maybe this part wasn't in the homework, but the more you produce, the steeper the slope gets once you get to producing overtime over 40 hours a week, or 40 sailboats, whatever it was. And what kind of function is that? Convex or concave? It's convex, and we were minimizing, and we did that in the linear programming homework, and it was fairly straightforward. Where things got complicated is when we said, what if overtime is cheaper than regular time, or if you could call it bulk discounts? And what did our function look like there? That was in the IP homework. And that, the slope gets less steep as you do more, which is a concave down function, and we were still minimizing, and that became a pain in the neck to solve, right? It's also good to think about this. Can we think of this as a minimum of, or maximum of, two linear functions? I have a linear function here and a linear function there, and I'm taking the larger of those two answers. So that's another way to formulate piecewise linear problems like this. And here this would be the minimum of two linear functions. So when we were minimizing a concave down function, we had to do a binary variable to keep it from doing the wrong thing. It's interesting to think about this in terms of the feasible region. So take a sec. I'm going to show you kind of a skeleton, and you can sketch the feasible region here. Take a sec to do that. So if overtime is pricier than regular time, which is what life usually works like, could I be in this part right here? There, I wouldn't be using all 40 hours of regular time, but I'd be using some overtime. Now, that doesn't sound feasible, but you know, if you tried to pay your employees like that, they would say that's feasible, right? Well, I only work 30 hours a week, but you're paying me 10 hours overtime, totally fine, right? So it's feasible, but it's not optimal for the manager. So optimal, potentially optimal, would be using 0 to 40 hours of regular time, and once you hit 40, then paying overtime. So this green border has the potential for being optimal and is feasible. But what if overtime is less expensive than regular time? So think about how this graph will change when we do that. All right, welcome back. So now, if I don't use all 40 hours of regular time and try paying cheaper overtime, the employees are not going to like that. So this is infeasible. The green border here is the feasible region. And is this a convex feasible region? No, it's not, because if you pick a point here and a point here, the line segment between them does not stay in the feasible region. So that's another reason why that was a hard program to formulate to optimize. Also think back to the problem where to send any flow at all on a road, you had to build the road first. What did that graph look like as a function of how much flow you send? So in the homework solution key, it looked like this. If you send 0 flow, you don't have to pay to build the road. If you send anything other than 0, then you have to you have to pay that $1,000 to build the road, and then incrementally for that. Is this a concave up function or concave down, convex, concave? You might be hesitating because we don't usually have functions with jumps in them. F double prime doesn't work here, as from a Calc 1 point of view. But if I choose a line segment, choose 2 points on the function like here and there, the line segment stays on or below the function. If one of my points is here and my other point is here, then my line segment stays on or below the function. So this is a concave down function, even with this discontinuity. And that was another hard problem to formulate, right? We were minimizing a concave down function. So we just said that. So all this knowing about whether a function is concave up or concave down can predict how hard it's going to be to optimize. All right, and then let's wrap up with linear programs. I mean, we're talking about nonlinear programs here, right? Well, can we think about them in terms of concave and convex? What's the linear objective function? Is that convex? Is that concave? Is it both? Is it neither? Well, if you picked any 2 points on a linear function and draw the line segment between them, it will stay on or above the function, right? So the function is convex. That line segment will also stay on or below the function, so a linear objective function is concave. So it's both convex and concave in our operations research way of thinking about things. So, well, and also how about the feasible region? Is the feasible region of a linear program convex or concave? Or sometimes not, I mean, feasible, we don't usually say concave. Is it ever non-convex? Well, it's just the intersection of a bunch of half planes or half spaces, and we said that's always going to be convex. So we are minimizing a convex function on a convex feasible region, so we can't get trapped in a local minimum, and we are minimizing a concave function on a convex feasible region, so the optimal solution will be at the corner points. So overall, this is the best of both worlds, right? We can't get trapped in a local minimum, and in some sense, I only have to look at the corner points to find the optimal solution. And I know there might be multiple optimal solutions along an edge, but at least we can find one of them at a corner point as long as the feasible region isn't entirely empty or our objective function isn't pushing us out to infinity. So the fundamental theorem of LP comes up again, and that will be one of the cornerstones of our next module.